This lesson is going to be on shells and orbitals. By the end, hopefully, we'll be able to state the number of electrons that can fill the first 4 shells of an atom, we'll be able to define an orbital, and we'll be able to describe the shapes of s and p orbitals. In a previous video, we discussed how successive ionisation energies provide evidence for the presence of shells and the number of electrons in each shell. So a shell is defined as a group of atomic orbitals with the same principal quantum number, n, also known as a main energy level. We usually use the word shell, but its meaning is equivalent to the energy level of the principal quantum number, so you can now see why we use the word shell instead. The first 4 shells hold a different number of electrons. So the first shell only holds 2 electrons. The second shell holds 8 electrons. The third shell holds 18 electrons, and the fourth holds 32. It's useful to bear in mind at this point that there are more than 4 shells that can be filled. However, we're only going to look at 4 shells in the sake of this example. There are rules governing where the electrons are allowed to be within each shell. We once thought electrons orbited around the nucleus, much like very fast planets orbiting the Sun. But electrons are not solid particles, and this planetary electron idea has now been replaced. It is now thought electrons occupy orbitals. They are regions around the nucleus in which electrons are found. An atomic orbital can hold up to 2 electrons with opposite spins. The shells we have spoken about before are made up of atomic orbitals. Each atomic orbital can hold a maximum of 2 electrons, as we've just said. If you imagine one electron as an electron cloud with the shape of an orbital, 2 electrons would be a cloud with the same shape but twice as dense. There are 4 different types of orbital: S, P, D and F. We've just mentioned that there are 4 different types of orbital: S, P, D and F. Each has a different shape, so we're going to now look at s orbitals. An s orbital has a spherical shape as seen in the picture. Remember we said the principal quantum number, n, indicates the shell that the electrons occupy. From n equals 1, i.e. the first shell, each shell contains 1 s orbital. This gives a total of 1 times 2, i.e. 2 electrons in each shell. So remember, each orbital can hold 2 electrons with opposite spins. You can rewind that bit and go over it again if you're still not quite sure. It is a tricky topic to get your head around. So the second type of orbital we are going to look at is a p orbital. A p orbital has a 3-dimensional dumbbell shape, which we'll show a picture of. The x, y and z in the diagram stand for the different axes of the 3-dimensional shape. In the same way that we said from n equals 1 upwards, each shell contains 1 s orbital, from n equals 2 upwards, each shell contains 3 p orbitals. We have px along here, py along here, and pz along here. So, in our second shell, we have 2 electrons in each orbital. We have 3 orbitals in total, so we have 3 times 2 equals 6 p electrons in our second shell. There are s electrons as well. We'll talk about that on the next slide. So we've just said in our second shell we have 3 p orbitals. Each orbital can hold 2 electrons, giving us a total of 3 times 2, 6p electrons. However, we said earlier that in our second shell we have 8 electrons, and that's because we've forgotten at the moment about our s orbital. So we said from n equals 1 onwards, each shell contains one s orbital. So our second shell contains not only our 3p orbitals, it contains one s orbital as well. That also holds 2 electrons. That gives us a total of 1 times 2 equals 2 s electrons plus the 6. So 6 plus 2 equals 8 electrons in our second shell. The structures of d and f orbitals are much more complex and aren't needed at AS level chemistry. From n equals 3 onwards, each shell contains 5 d orbitals. This gives us 5 times the 2 electrons that each orbital can hold, 10 d electrons. From n equals 4 upwards, each shell contains 7 f orbitals. This gives us 7 times the 2 electrons each orbital can hold, 14 f electrons. So we're now going to look at the third shell, get into the swing of talking about orbitals. So we said from n equals 1 to the first shell upwards, each shell contains one s orbital. Each orbital contains 2 electrons, so we've only got one here. That gives us our 2 electrons, and they're spinning in different directions. We said from n equals 2, the second shell upwards, each shell contains 3 p orbitals. Each one of those 3 holds 2 electrons. That gives us 6 p electrons in total. Next one then, we said about d orbitals in the last slide. So from n equals 3 upwards, the third shell, each shell contains 5 d orbitals. So same as the 3p orbitals, each one of those 5 d orbitals holds 2 electrons. 5 times 2 gives us the 10 d electrons. So let's top that up then for the third shell. We have 2 plus 6, that equals 8, plus the 10, we have a total of 18 electrons in our third shell, which was the same value as we saw in the table at the very start of the video. Let's just run through the fourth shell then quickly. We have our 1s, 2 electrons. We have our 3p, that gives us 6 electrons. We have then our 5d, that gives us 10 electrons. And our new one that's coming in then, we have our 7f. So same as before, 2 electrons per orbital. We have 7 f orbitals, that gives us 14 electrons in total. So the 18 electrons from before plus 14 new ones, that gives us a total of 32 electrons in the fourth shell. So next question, you're probably wondering, how do we represent the different electrons in orbitals? They've got such weird shapes you don't want to be drawing them out all the time. They're very complex. So what we usually do is we often represent an orbital as a box. Each box can hold 2 electrons. So this is called electrons in boxes. Very simple. Now we said before that each electron in an orbital has a different spin. So we then represent our boxes as such. The first electron in the orbital goes in like this, or the arrow the other way up, doesn't matter. The second one spinning in the opposite direction like that. So you could also have it drawn like this, that's fine. What's not allowed is drawing it as such. So we can't draw it both spinning in the same direction. They're not allowed. They've got to be spinning in opposite directions. So why have they got to be spinning in opposite directions? So as you recall, each electron has a negative charge, and we'd expect the 2 electrons in an orbital to repel each other. An electron, however, has a property we call spin. Each of the electrons in an orbital must have opposite spins, which we represent then using the arrows. Because the electrons have this property called spin, they don't repel each other in the same way as we would expect to see if they didn't have this property. However, that's far more complicated than we need to know at this level of detail. So, what actually is an electron? The answer to that question isn't easy. We don't even know the exact position of the electron, even within the atomic orbital. In some ways, electrons are particles, but in others they behave as a wave. And even then, we can't be certain where they are. So it's very difficult, if not impossible, to visualise exactly what an electron is. However, one thing is certain. The idea that an electron is like a tiny planet whizzing around the nucleus is not true. Luckily, we're not too concerned with the exact properties of an electron at this level of detail. However, chemists in general do use information about atomic orbitals and electrons when describing the behaviour of atoms, when looking at how elements react, and the structure of the periodic table. So, to finish off then, how do we use this electrons in boxes idea with the different types of orbitals? So, with our s orbital, we have 1 in each shell from n equals 1 onwards. That can hold 2 electrons. We then have 3 p orbitals, so 3 boxes, and they can hold 6 electrons. And that's from the second shell onwards. Thirdly then, d orbitals. We said we could have 5, so we need 5 boxes, and that can hold 10 electrons. Lastly then, the F, we have 7, 4, 5, 6, 7 F orbitals, and they hold 14 electrons. So, if we fill these up, we would say we had 1, 2, 3, 4, 5, 6, and so on. So these electrons in boxes here, if we were to fill in all the electrons, would represent 4 shells. That's it for today. We have learnt about the different orbitals. We have learnt about the 4 different types, S, P, D, and F. We've learnt about spin and how we represent these orbitals by drawing electrons in boxes. We've learnt how the electrons in the orbitals match up to the number of shells. We can also hopefully describe the shapes of the s and the p orbitals. They're the main ones we look at in A-level chemistry.